I know. It's a capital K, though. Okay, so clear your palette of rate law expressions. Rate law expressions. And now we're going to deal with chemical equilibria. Equilibria is the plural of equilibrium. Okay, so chemical equilibria. So we've kind of talked about equilibria before, and that's all about a reaction going in the forward direction and the reverse direction. And we're kind of, this is what, Unit 2. We're kind of setting ourselves up for, this is Unit 3. We're kind of setting ourselves up for, in Unit 4, to finally talk about acid-base, acids and bases. Now, I know clear back in junior high, they talk about acids and bases, right? Okay. But we need to talk about them kind of a little bit in terms of chemical equilibria. So it really has practical implications. So an equilibrium goes in the forward direction and the reverse direction, but we still kind of talk about left-right reactants and products, even though it goes back and forth. I know it seems kind of silly. And I think this was the equilibrium I put up there before, or I talked about before, where this is why your yields aren't 100%, because it goes back and forth, okay? And I love equilibria. They're awesome. So I'm going to kind of draw your attention. These are 3 different scenarios for this same equilibrium down here, okay? So we have reactants over here, 2 reactants, and we have the product over there, but it goes back and forth. These 3 scenarios, okay, of course you have time along the x-axis for all of them. Notice that in this first case, we have the 2 reactants and no product, okay? Oh, does that thing keep just, oh my goodness, just ignore it. In the middle case, look, we don't have any reactants and we have all product. It can happen, right? Okay, and in the last scenario, we have a little bit of everything, okay? And I just think that is so cool. And we'll be talking more about this, but the cool thing about chemical equilibria is they kind of find their own little niche. Okay, so the gray parts here are where it has established, it's basically flatlined. It's like, dude, finally here in the gray area for each one of those 3 scenarios, you're like, oh, it's constant. Okay, not to say it's not dynamic in that it's still going back and forth, but the concentrations of the reactants and the products are constant. Okay, is that for me?
Yeah.
Okay. Thank you. Do you have anything to Hayden?
I almost have it all done. I just have to finish writing my write-up.
Except the what?
The write-up.
Okay.
I have to just do one more paragraph on that.
Okay.
Will you be here? Do you have office hours today, or are you taking up right after?
I got an appointment in Burlington, but if you slip it under my door and it's there when I get back Monday after break, I'm cool with that.
Cool.
So that works, but it has to be under my door, and I get here Monday about, usually about 9, it's the earliest.
Yeah, me and Quinn should be here in a minute. We were in the library working on it. The library clock must be slow or something.
Okay. Yeah, I just know that I need to get to a certain point in this lecture, so I was like, I gotta go.
Oh,
I gotta go.
Sorry.
That's okay, no big deal. So I said before we started, clear your thought of rate law expressions. Now we have another expression, okay? It's called an equilibrium constant expression, and it has a letter K, but it's a capital K. So we're not about rates now, we're all about chemical equilibria. And specifically, we're going to be looking at not the rate at which the equilibrium is established. We're going to kind of assume it's already at equilibrium. But we're going to be looking at the concentration of the reactants and the products. Okay, their mathematical relationship. It's so fun. I love it. This makes me smile. It just does. I'm not the one who came up with it, but I mean, obviously, I just think it is so cool how it works. So we have this generic expression where we have 2 reactants and 2 products in chemical equilibrium. So the lowercase letters are the stoichiometric coefficients of those reactants and products. So there is your first equilibrium constant expression. And it is different than your rate law expression. There on the left is your equilibrium constant. K sub C, it's a capital K. So like when I was grading your tests, I was like, you guys got to be careful in making sure that the other K we talked about in Unit 2, the rate law constants are lowercase k, and these are uppercase K. So of course we talked about the brackets, those are molar concentrations, right? Molar concentration of the products, molar concentration of reactants, and like I said, those little letters, the A, B, C, and D in front of the species of reactants, products, those little letters are stoichiometric coefficients. Now again, you have to clear your palate, as I know you guys really crammed to try to make sure you did well on the Unit 2 exam. But now these are not reaction orders, okay? These are different. So notice that we do finally get to do what some of us wanted to do with our reaction orders. We do get to, in your equilibrium constant expression, the equilibrium constant is equal to in the top we put products, in the bottom we put reactants. Okay, so it's a ratio of products to reactants, and there's their molar concentrations, this time raised to their stoichiometric coefficients. So go ahead and make that hardcore in your brain. That's what we got.
Okay, that makes it so much easier.
Yeah, but the final's comprehensive, and you need to be able to kind of draw a line, and yeah, yep. Equilibrium constants, K sub C's. We're going to talk about K sub P's here in a minute too. But they are temperature dependent. Not so surprising. Okay. And remember that the equilibrium constants are, I could go back to that slide where we had showed the equilibrium, the different amounts. And what's so funny?
No, it's fine. Yeah.
Okay. We could go back to that slide with the different amounts, the gray areas where the equilibrium concentrations have been met. That's what you got to picture those molar concentrations. These molar concentrations on your equilibrium constant expression. Okay. Okay. Now this talks about your equilibrium constant expressions will be valid unless you stress the system. And I don't know if you remember, we talked about the Chatelier's principle back when we talked about stressing this system that's like solubility and by changing the temperature and stuff like that. If you stress it, you get a different equilibrium. But if it's at the same temperature, it's the same Kc. So they kind of scramble a little bit. So the number comes up to the same Kc. Now I'm all about dimensions, okay? Like units, like our rate law constants, they had to have specific units. I'm going to tell you that all K's, your equilibrium constant, your K's are unitless. Like Mrs. Snipes, what the heck? And actually it comes about because we kind of normalize them based upon the same unit, okay? So, and I refer you to your textbook if you want a brief look at that. So this kind of looks at what I mean by kind of making the units cancel. The C naught there is kind of introduced as just like a unit factor, the number one, basically, with the units that will cancel out. That's all that is. Okay. All right. But if we go back to here, I guess this is our first look at well, I guess that's not a very good example. We're going to have a better one coming up. Okay. So your Kc is a relationship of your reactants. Wait, darn it. Products. Products in the top, reactants in the bottom. Products over reactants. All raised to their stoichiometric coefficient. So does this make sense? If your Kc is very large, that means your numerator is very large. That means your products is very large. Okay? That means that it favors the formation of products at equilibrium. If your Kc is pretty small, then that means your products is small, but your reactants is big. And that means it favors, actually at equilibrium, the concentration of your reactants. Intermediate values, and those would be between 1,000 to 10 to the minus third. Intermediate values means, at equilibrium, you kind of have a fair amount of both. And by big, I mean big, and by small, I mean very small. Okay. So kind of let the dust settle and let it reach chemical equilibrium, those gray areas, and see what we got. Those are equilibrium concentrations. So by big, I mean 1.4 times 10 raised to the 83rd power. You're like, are you serious? That is a humongous number. That means that the products are very favored. In fact, to me, and we kind of get into this a little bit, is this equilibrium, I'm thinking you could just simply do that, a one-way arrow, because dang, that pretty much goes to completion as far as I can tell. Pick one that's small, this one right here, okay? The fact that it's very small and we have products in the numerator means that we have a lot of reactants left. So this one just does not want to go that way very much. Instead, it goes this way. You know what I'm saying? How that goes, okay?
So is the KP the same as the K?
KC, KP, and say, they are different. They're related.
Okay.
Yeah, and we're going to talk about KPs coming up. Like here, they didn't, oh, I see KP. Yeah. KPs, I didn't catch that. KPs deal with stuff that's all in its gaseous phase, or stuff with partial pressures. I have a slide coming up, and it's kind of weird, but if anything in its solid state doesn't appear in the equilibrium constant expression. So this would be the partial pressure here. Yeah, KPs and KCs are related. And we'll kind of talk about that. All right. So now you get to give it a try. So it's always in the numerator, it's products, and in the denominator, it's reactants raised to stoichiometric coefficients. So we could write the Kc expression for this. I call it Kc, it's equilibrium constant expression. Kc expression would be equal to the molar concentration of ozone, O3, raised to the second power, divided by the molar concentration of O2 raised to the third power. That's it. That's your Kc expression. There would be a Kc value associated with a specific temperature, and that would relate the molar concentrations of O3 and O2 at equilibrium. Here's another one for you. Okay, so it's always products over reactants. So it would be the molar concentration of NO2 raised to the fourth power times the molar concentration of H2O raised to the sixth power divided by the molar concentration of NH3 raised to the fourth power. Also in the denominator, the molar concentration of O2 raised to the seventh power. Are these already there?
What?
Are these already written down?
Yes.
Okay. That's it. Okay, again, these are equilibrium concentrations. Hey, Queen. So there are a few extra important things to keep in mind, extra guidelines. One of them, we've talked about chemical equations. If you see the word, the kind of AQ, that means that it's an aqueous solution. And so a special kind of caveat about that particular species is if you have anything, if you see AQ anywhere, and you have water as either a product or reactant, water does not appear in your Kc expression. So here's an example of that one. The AQ gives it away. We're definitely dealing with this equilibrium occurring in water. So that H2O there on the reactant side with the L next to it, it's not going to appear in our equilibrium constant expression. So that's why this one looks like this. Again, it's products over reactants. So ammonium raised to the first power times hydroxide raised to the first power divided by ammonia, NH3, also raised to the first power because that's a stoichiometric coefficient. Okay, so that's something to kind of put in the back of your mind. That's an important aspect of writing equilibrium constant expressions. For this particular equilibrium, does it favor the reactants or the products? Small, so it favors the reactants. Yep, favors the reactants. Yep. So here's another thing for you. If you see an L or an S next to a species, it doesn't appear in your equilibrium constant expression either. And kind of the thought there is if you have a chemical equilibrium and you have literally an L or an S, liquid or solid, its concentration is relatively constant. It's kind of how I've heard it. Okay. So here's an example of that one. So again, S or L, solid or liquid, it doesn't appear in the equilibrium constant expression. So this one actually kind of simplifies to there's nothing in the denominator now, is there? Because we have silver chloride, solid. So this one actually just is the molar concentration of the silver plus 1 cation raised to the first power, its stoichiometric coefficient, times the chloride ion also raised to the first power, okay, is equal to Kc. Okay, so solids and liquids don't appear. Water doesn't appear if it's occurring in an aqueous environment. What do you think? Favors the reactants? The reactant? Okay. And this is a good example. We're going to talk about solubility of compounds, salts. Okay, so if it favors, this is just trying to dissolve that darn silver chloride solid in water, trying to get it to break apart and form your silver ion and chloride ion. And if it favors the reactants, can you see where the solubility is pretty low? That's actually kind of what this is talking about. Okay, so I'm just going to push these out there. I'm not going to take a look at them now because I want to get through KPs. Okay. So, go back to KCs. I want to talk about KPs. Do you guys have this slide? Is this kind of a repeat slide?
It's a repeat.
It's a repeat. So this actually is your equilibrium constant expression, where equilibrium constant Kc is equal to, it's always products divided by reactants, their molar concentrations raised to their stoichiometric coefficients. It is temperature dependent, and these are equilibrium concentrations. I'm going to take you through a proof now for relating Kc's to Kp's. The K kind of gives it away. They're both equilibrium constants, but the C, think of C as molar concentrations and P as the relative partial pressures. Okay, so Kp is going to look at the partial pressures of the products and the reactants. All right. So Kp is all about partial pressures, but it takes on a very similar pattern as your Kc expression. So it's the partial pressure of the products raised to their stoichiometric coefficients divided by the partial pressure of the reactants raised to their stoichiometric coefficients. I'm going to kind of walk you through how they're related. Well, just as I said, Kc ends up being unitless, also Kp is unitless for the same reason. All right. So let's consider an equilibrium where everything's in their gas phase, and we know molar concentrations, and we know partial pressures of everything. So our Kc expression in molar concentrations looks like we've been talking about. Now, if we take the ideal gas law equation and rearrange it for molarity, molarity is moles per volume, so N per V. So rearrange this, and you get N over V is equal to PRT. So if you have something that's gas phase and you know it's molarity, this actually relates molarity to partial pressure. Well, there's our Kc expression for the equilibrium of interest. Now, if we substitute those molar concentrations for their partial pressure over RT, like we can do, that's legit, then our Kc expression in terms of partial pressures becomes this, where the Kc in terms of your equilibrium constant in terms of molarity is equal to your partial pressures divided by RT. In each case, we have to raise them to their stoichiometric coefficient. Now, we've done a little bit of canceling, and I was like, well, yeah, that's pretty cool. We'll just cancel out all those RTs. But you cannot, even though R is a constant, it's all the same temperature. The reason you can't is because they don't necessarily cancel. Like the number of terms of RTs up here might not be equal to the number of the RTs, one over RTs down here. Okay, if you had stoichiometric coefficients of 1 across the board, yes, they could all cancel. Okay, but what if you had 2, 2, 1, and 1? Then you'd end up with, extra terms of 1 over RT up there. So the way we get around that is, looks like this. It didn't strike me until just like last night when I was getting ready to do today's lecture. I'm like, oh yeah, that makes sense. So we're going to pull out that term, 1 over RT, and we're going to leave the partial pressures. We need to distribute the exponent through both of those, okay? So now we can gather our 1 over RT terms and our partial pressures, and it looks like this. So this is gathering our partial pressures, again raised to their stoichiometric coefficients of the product, stoichiometric coefficients of the reactants. Now we have this thing, this 1 over RT, and basically it is the sum of C plus D, that's the stoichiometric coefficients of your products, minus the sum of the stoichiometric coefficients of your reactants. So there again, if I said, like, if they were all 1 across the board, then you'd have 1 plus 1 minus 1 plus 1 is 0. And then you'd have this term raised to the 0th power, which is 1. So at that point, you definitely still, or how do I say this? Your Kc is equal to your Kp then. It totally is. Okay? So the exponent of the 1 over RT term, we can actually just call that delta N, where delta is change in, and this is the change in moles from our product side compared to our reactant side. Okay, so your equilibrium constant in terms of molarity is equal to your equilibrium constant in terms of partial pressures times 1 over RT raised to the delta N. I think I have one more thing coming up here. So I have a few more things. But this is a link between the two. Trying to kind of get it into even a better form, we can rearrange that and get Kp is equal to Kc over 1 over RT raised to the delta N. We can kind of take that 1 over RT raised to the delta N. We basically have a fraction in the denominator, which is kind of dumb. So we can go ahead and, what did I do here? I guess I just kind of cross-multiplied. But anyway, finally we have a blue box. And this blue box represents something that you can kind of take to the bank and use. The relationship between the equilibrium constants and partial pressures versus molar concentrations. So if your delta N is none, then they're equal. I think we're going to do an example coming up then. The value of R we're going to use is that one we used with gases, the 0.082058 liters atmospheres per mole Kelvin. So if we're using that constant, then we need to make sure our partial pressures are in units of atmospheres. Okay, so let's work a problem and see what it looks like. Well, we have Kp, but we want Kc. So remember, these equilibrium constants are unitless. So it's weird to look at it as simply Kp is equal to 0.62. I know that's strange. They do depend upon temperature, so we're going to hold it at 45 degrees Celsius, and we want to compare or get to Kc. So from that blue box, we can rearrange it. The delta N we need for the blue box, remember that's the change in stoichiometric coefficients. Deltas are always final minus initial, so it's the same thing here. It's going to be the final sum of the final stoichiometric coefficients, the products, minus the reactants. So in this case, it's 2 minus 1, which is 1. The temperatures need to be in Kelvin, so we're going to jack that 45 degrees Celsius up by 273 units, and we get 318 Kelvin. So rearranging this now to solve for Kc, because we have Kp, it looks like this. So Kc is equal to Kp divided by RT raised to the, in this case, first power. It's not too bad. Your equilibrium constant then in terms of molar concentrations is 0.62. And it's weird to see, I don't have any units here, but I guess I don't care about units in this case because my equilibrium constants, whether it's C or P, are all going to be unitless. So 0.62 divided by 0.082058, that's your R, times your temperature, and that's 318 Kelvin. I guess if I was probably doing this on paper, I would include my units, even though it's going to be unitless over here on the left.
So is that what you want us to do for our homework then, is including it?
That looks naked to me, yeah.
Okay.
But I'll take either way, because I did it this way on my, I did it this way on my slide, so I'm okay either way for this one. My fear is though, and I saw it a little bit on on your exam, your work was getting a, I don't want to look at anybody in particular, but you know who you are, that your units are getting sloppy, and it's not just for me, although it's Friday. It pisses me off that you don't use units. It also disturbs me because I think down the road it can really screw you. So if you get to be an engineer out there and, you know, the problems get even harder. And if you don't make sure your units are getting you where you need to be, yeah, that could be really bad. So the delta N, of course, we said was 1, and there's your delta N. So, yep, your Kc is unitless just like your Kp was unitless. And we get a value of 0.024. And again, what does that do? It describes the equilibrium molar concentrations. Okay? Yay! That's how far I wanted to get. I was so paranoid I wouldn't have enough time. So I'll push these out there then.